Hi, my name is Mohammad Fatahi, and I am a researcher at University of Tehran. Due to my interest in machine learning and control engineering, I have a plan to share my experience and knowledge in this area of research in some lectures. So I will talk about optimal control techniques like LQR or LQT or so on, and the application of reinforcement learning techniques. Uh, model-based techniques and model-free techniques like Q-learning in this area of research. And then I will talk about PID and MPC and imitation learning, which are quite popular techniques these days. And um, I will investigate the performance of these techniques and some practical systems like double inverted pendulum or a car. At first, we should know what is the optimal control. Optimal control is a condition of dynamic systems that satisfy design objectives. Some widely used optimal control techniques are linear quadratic regulator, LQR and LQG, and model predictive control and H infinity. You can access further information regarding optimal control with the mentioned link. Okay, let's start with LQR. LQR can give us an appropriate balance between system state regulation and at the cost of control actuation. But the question is that how it works. For calculating the the optimal policy, we should have the dynamic of our system, which can be challenging in some tasks. Additionally, um, we have a cost function which is based on the states of our system and the inputs. And after some calculations, we reach um, the Riccati equation, which can help us to calculate the optimal policy. But the calculating this equation can be impractical for large scale systems because it has a computational burden. And there are some challenges regarding the LQR, and I mentioned two of which before, but there are more challenges. It is sensitive to modeling errors and it is limited just to linear systems. I applied the LQR to the double inverted pendulum to show you how we can implement this strategy to our custom model. At the first step, we should calculate the linear system because you can see it is necessary to calculate the linear system because um, LQR just perform on linearized models. And at the second step, we convert continuous model to discrete, which can be performed by C2D command in MATLAB. And at the third step, I solved the Riccati equation with IDER command in MATLAB. But there are two tips that we should consider about this example. Firstly, you can see over time our states converge to 0, which is our desired value, and we can adjust it to any desired that you like. And secondly, in control signal, the maximum value is 20, which is a rational value for this task. I said that calculating the Riccati equation can be challenging. So how we can overcome this challenge if we face it? There are two ways to calculate matrix K in optimal policy without using the Riccati equation. Firstly, policy iteration, secondly, value iteration. But these two methods perform offline, and this is another challenge. And policy iteration and value iteration are model-based RL algorithms. To replace Riccati equation with policy iteration, we should follow 3 steps. At the first step, we have policy evaluation. In this step, we first determine an initial policy which should be feasible. I mean that all poles should be in a unit circle, which can be implemented by place command in MATLAB, and then we determine matrix P, which can be implemented by fmincon command in MATLAB. In this step, we should solve an optimization problem to reach matrix P, and the second step, we have improved policy. In this step, respect to obtain P, we will update K with the second equation, and we will repeat this cycle to reach the stop condition, and you can see the results in this page, and I show how matrix K parameters converge over different iterations. To replace Riccati equation with value iteration, we should follow 3 steps. At the first step, we have policy evaluation, in which we initialize K and P matrix to find optimal P matrix, and then we have improved policy, and in this step we use the second equation to find optimal policy, and we repeat this cycle, and you can see the results, and value iteration outperform policy iteration because I think its convergence has occurred faster than policy iteration. Thank you for your attention. I will continue to talk about the applications of reinforcement learning in control engineering, and I will focus on model-free techniques, especially Q-learning, in the next lecture.